Hi everyone, welcome to our very last lecture of Summer Session 1, ESS 3, Oceanography. I cannot believe we are already at the very last lecture of this whole course. So today we're going to talk about climate change. We're going to go over why does climate change, how has climate been changing, and then what's it going to look like in the future. We're going to talk about ocean acidification and sea level rise, so the two big climate change issues in our oceans. So for the first part of today, we're going to go over the Earth's energy balance. So looking at the diagrams of Earth's energy balance, what's coming in versus what's going out. We're going to talk about how climate changes and why in terms of the energy balance. So how and why does climate change due to different components of that energy balance on Earth? And then look at the past 100 years, how climate has changed and why. And then look at some recent observed changes in climate. So we'll look at atmosphere, precipitation, cryosphere, and our oceans. So the way that climate is changing. So the climate of our Earth is a system. So everything is constantly interacting. The oceans with the land, with the atmosphere, with the magma down in our mantle. Everything is interacting. There's a constant exchange of energy. Our climate system, really, we say, is characterized by change. So everything is moving and interacting all the time. So where does our energy come from? So the energy from Earth starts at the sun. So here's our sun. The sun emits an absolutely massive amount of energy. So the luminosity of the sun, get this number down here, that is a lot of zeros. That's 10 to the 26 watts order of magnitude. The sun provides a lot of energy. So when that energy comes towards the Earth from the sun, it is in the form of shortwave radiation. So it's a shortwave radiation. It is in the visible part of the spectrum, so it's visible light that comes in from the sun to the Earth. Of the light that is reflected, is moving from the sun to the Earth, about a third of it, 30%, is reflected away from the Earth before it even reaches the Earth's surface. So almost a third of all of the energy that the sun is sending us actually gets reflected away by our atmosphere. So that's what these clouds are. This cartoon is saying the clouds are our atmosphere. About 30% of all of the incoming solar radiation actually is reflected back out to space before it even hits our atmosphere. The remaining 70% makes it through the atmosphere and does hit our surface. So remaining 70% is travels through the atmosphere and it is absorbed by Earth's surface. So why doesn't Earth get hotter and hotter and hotter and hotter if we are constantly, all the time, absorbing all of this 70% of this many watts of energy coming in from the sun? Why aren't we constantly getting hotter, 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 hotter? Because there's more to the diagram. So there's also outgoing energy from Earth. So Earth has a temperature. We have a temperature. We are not only absorbing energy, incoming energy from the sun, we are also radiating heat back out to space. So the heat that is radiated back from Earth's surface is in the infrared, so it is a longer wavelength than the incoming shortwave energy. We are also radiating heat back out. So what happens is some of the energy that we are radiating back out to space actually will be absorbed within our atmosphere. So some of the energy that we are we are radiating back out to space in order to cool the Earth back down, keep it from heating up all day long, all the time, over many, many days and years. It will actually be radiated in our atmosphere. So there's certain gases, which you might have heard are called greenhouse gases, that actually absorb the energy that we are radiating back out to space. So instead of the energy from Earth's surface all making it out to space, some of it is actually captured. We say captured, but it's absorbed by gases in our atmosphere. So we say that the longer wavelengths, the outgoing long wave radiation, is actually trapped by our greenhouse gases. So not all of it, some of it escapes. But our greenhouse gases, the greenhouse effect essentially, is causing a net warming effect. So the fact that we have these greenhouse gases capturing some of the heat that Earth is trying to get rid of, we have what we call a net warming effect. So overall, our atmosphere is warming. So what are these greenhouse gases? There's certain gases in our atmosphere that can absorb the outgoing long wave radiation from the Earth's surface. So the most important is water vapor. So water vapor actually makes up the majority of our greenhouse effect. Also because there is a lot of water vapor. Carbon dioxide is another. You might have heard of this. It is where we are causing the most problems. So carbon dioxide has the greatest contribution from humans from burning fossil fuels. So the burning of fossil fuels emits carbon dioxide into our atmosphere. But carbon dioxide does also exist naturally. We happen to just be adding an unbelievable amount of extra carbon dioxide to our atmosphere. The strongest, I would say, greenhouse gas is methane. So what I mean by that is methane actually has the greatest warming per molecule. So each molecule of methane is a very, very, very strong, powerful greenhouse gas. Methane is the second most abundant greenhouse gas that we contribute as humans, mostly from landfills, so decomposition of our landfills, and from cattle. So cattle release a lot of methane into our atmosphere. So where we have farms raising cattle, we will be producing quite a bit of methane. There are other gases that are greenhouse gases, but these three are the main three. So water vapor, carbon dioxide, and methane. And as these concentrations of these gases in our atmosphere increase, the strength of our greenhouse effect trapping the heat that's trying to escape is going to go up. So the more gases we have in our atmosphere, the more greenhouse gases we have in our atmosphere, the stronger the greenhouse effect will be, the more heat will be trapped and kept in our atmosphere. So the greenhouse effect is causing this net warming because we are increasing the amount of greenhouse gases we have in our atmosphere. But is the greenhouse effect always a bad thing? No. So the Earth's temperature, if we did not have the greenhouse effect, would actually be freezing. Would be so cold. It would be below freezing by almost 20 degrees Celsius. So if we had no greenhouse effect, the average temperature on Earth would be below freezing. However, with our fabulous greenhouse effect, the average temperature on Earth is about 15 degrees Celsius, so 60 degrees Fahrenheit. Much more comfortable than 0 degrees Fahrenheit, I might say. So our greenhouse effect actually is one of the very, very, very important reasons that Earth is habitable. So the reason that there's life on Earth is because the temperature of Earth allows for it. So because of our greenhouse effect, the temperature on Earth is warmer. However, what we are doing we being humans are doing now is we are adding way too many greenhouse gases to our atmosphere. So this greenhouse effect, the warming, is just going to keep increasing. So this greenhouse effect is going to get stronger and stronger and stronger and stronger with the more greenhouse gases that are in our atmosphere, meaning that the temperature of our Earth is just going to keep going up and up and up. So that is global warming, where our greenhouse effect is getting stronger and stronger, meaning the temperature on Earth is going to go up and up and up and up and up until we make some serious changes. So why exactly does our climate change in terms of history of Earth? Why has climate changed in the past? So there's many different ways. I'm going to go through quickly some of the main ones. So the first thing that can change is the amount of energy that's coming in from the Earth. So the amount of incoming shortwave radiation can actually change due to changes in the sun's luminosity, so changes in the brightness of the sun, or due to changes in Earth's orbit. So there's certain changes that happen on very, 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 very long time scales due to Earth's orbit changes. That is going to change the amount of incoming radiation we receive from the sun. Another thing that can change is the amount of that incoming radiation from the sun that gets reflected. So what is reflected back from our atmosphere, as well as some sunlight is reflected right back off of our surface. Remember, it's 30% of the incoming solar radiation, about 30% of the incoming solar radiation is reflected before it can be absorbed. That 30% can change. So this can be caused by changes of the atmospheric composition, so increased or decreased aerosols in our atmosphere. Usually this is caused by volcanic eruptions. So large volcanic eruptions can add a really large amount of aerosols into our atmosphere. That's going to change the amount of sunlight that's reflected, as well as changing the clouds. So changing either the type of clouds or the amount of clouds that we have is also going to change the amount of energy that is reflected by those clouds. And then changes in surface type on Earth. So this little 5% of the sunlight that is reflected right off of the Earth's surface would be reflected off of something very bright, like ice or snow. So as that ice and snow changes, we're going to have a change in reflection, a change in the amount of incoming radiation that is reflected. So here's a question for you, first one of the day. If I warm the Earth, then ice and snow will melt. So as Earth is warming, our ice and our snow are melting. Which of these is true? So what will the melting of ice and snow cause in terms of our energy budget? So if we think about ice and snow, they're very, very bright. If you've ever gone skiing, you might have been unfortunate enough to get a sunburn or at least a suntan around your ski goggles, and you end up looking like a raccoon after you've gone skiing. This has happened to me many times. So I can tell you, ice and snow are very, very bright. What happens is, if we change the amount of ice and snow on the surface of our Earth, we're going to change how our sunlight is reflected. So if we remove ice and snow, remove that really bright surface, we are going to cause there to be less reflection of light. So less bright surface means less light will be reflected. So less of the incoming energy is going to be reflected, which means that there will be more warming. So instead of that incoming energy being reflected right back out to space, we're actually going to have the surface that is no longer covered in bright ice and snow absorbing that energy. So if we remove ice and snow from our surface because of increased warming, we're going to cause there to be less reflection and therefore more warming. So it's just going to increase our warming even further. So another way that climate has changed or can change is due to the amount of this long wave radiation that is absorbed in our atmosphere. So this, of course, has to do with our greenhouse gases. So changing the amount of greenhouse gases in our atmosphere is going to change our climate. So this can be natural. So changes in aerosols due to wildfires, for example. Not saying all wildfires are naturally occurring. Most of them are not. This can also be due to greenhouse gas concentration changes. So those are mostly caused by humans lately. So if we think about how our climate has been changing in the past, you can see here, this is a graph that shows, it's really nice because it breaks down the different components of climate change into the warming components and the cooling components. So what has been going on to cause warming versus cooling. As you can see, there's a lot more on the warming side, which is why we know our atmosphere has been warming. So here we have our greenhouse gases. So we've had an increase in greenhouse gases, also an increase in some aerosols and clouds. So the net effect of all of these changes, the largest being our greenhouse gas increase, has caused warming of our atmosphere. So where is the additional carbon coming from? So both methane and carbon dioxide have carbon. That carbon is what is entering our atmosphere and causing most of this anthropogenic climate change. So it's due mostly to fossil fuel burning. So burning of fossil fuels, which is the way that most of our society runs. This adds like 6 to 7 gigatons of carbon per year to our atmosphere, as well as deforestation. So deforestation has been pretty horrible because trees remove carbon from the atmosphere. So trees need carbon dioxide. So when there are a lot of trees, we will have a lot of carbon dioxide removed from the atmosphere. If we get rid of trees with deforestation, that carbon dioxide is no longer being removed. So not only are we adding carbon to our atmosphere, we're also removing the main way that carbon is generally removed or cycled in our atmosphere. So we're adding to it, and then we're removing the sink. So with deforestation, we're getting rid of the natural way that Earth could remove atmospheric carbon. So how has our climate been changing so far? In terms of the atmosphere, between 1880 and 2012, we've had a 0.86 degree Celsius warming. That is continuing to increase. And it's likely that this increase in global temperature has also increased the frequency of heat waves in Europe, Asia, and Australia. And it is most likely that recent times are actually hotter than any other time in the last 1,300 years. So this is a very big change that has not been seen in recent past. Here is an image that shows historic temperatures throughout the year. So right now we're in the 1940s. And as the color gets closer to red, it's more warming. So you can see we are almost at that 1.5 degree change in temperature compared to 1850. This figure is nice. It has the 1.5 degree and the 2 degree change outlined there. So you can see that pretty steadily throughout time. The circle's getting bigger, meaning our atmospheric temperature is increasing. Oh, excuse me. So this is a graph of observed surface temperature change from 1900 to 2012. So take a look at this graph and try to decide where's the only place on Earth that has had a significant cooling trend. So using the scale on the bottom, you can see that a change in temperature on the cool side would be in the blue colors rather than the red and the purple. So the only place here is right here in the North Atlantic. So the North Atlantic Ocean has experienced a bit of cooling, whereas almost everywhere else on Earth has had warming. You'll also notice that the largest amount of warming is on the big continental interiors away from our oceans. So the continents are warming. The continents are warming more, especially the interior of those large continents. If you remember, our ocean has a moderating effect. So the oceans, the specific heat content of our oceans allows for the oceans to actually minimize the change in temperature due to the amount of heat it takes for the ocean to actually change temperature. So the highest temperature changes that we see are going to be furthest from the ocean in the center of our large continents. So if we think also about precipitation, so it's not only temperature changes that we've seen, but also precipitation. So in terms of precipitation with climate change, we are seeing and then further expecting what we say is increasing the extremes. So it's places that are generally wet are going to be more wet. Places that are generally dry are going to be more dry. So that means more frequent droughts, more frequent and more extreme droughts, as well as more frequent and more extreme flooding. So increasing those extremes is what's happening with our precipitation. So if we look at the cryosphere, so the cryosphere being ice on Earth, the glaciers on Earth and as well as snow cover have declined in both the northern hemisphere and the southern hemisphere. We're seeing record losses of mass of ice from our two ice sheets, Greenland and Antarctica. And we're also seeing a decline of sea ice on Earth. So here is a graph here that shows Arctic sea ice extent, meaning how much sea ice there is in the Arctic Ocean. And that is decreasing as our temperatures are warming. We're seeing this trend of decreasing the amount of sea ice, which then is expected to increase even more in the future. Here's a picture, well, a series of pictures taken from the same location of this glacier. So back in the early 1900s, this glacier, or this fjord, was entirely covered in this glacier, flowing all the way out of the image. About 50 years later, the glacier had retreated. There was a lot less ice, so the glacier front was actually right here. And in a more recent picture, I think this one was 2007, you can see the glacier is only visible way, way, way in the back. There's actually no ice in this region anymore. So we're definitely losing ice on Earth as our temperatures increase. So, of course, in this class, now we are going to talk about our oceans. So in terms of oceans, how have our climates been changing? The temperature of the oceans has increased. So oceans warm at the surface because our atmosphere is warmer, but we've also seen warming even at 300 meters depth. the oceans are incredible in so many ways, but they've also taken up about 90% of the extra energy that we've had between 1971 and 2010, and that is still increasing, but that's those are the published numbers. So the ocean actually absorbs about 90% of the extra energy that our greenhouse effect is causing. So a lot of our increased energy, we can see here where this extra energy is actually going. So you'll notice that the two blue colors are separated into the upper ocean and the deeper ocean. So our ocean is absorbing the majority of the extra energy that we have. So the ice, the land, and our atmosphere make up a very small, only 10%, where the oceans are actually absorbing 90%. So the oceans are taking most of the brunt of this issue with our global warming. So in addition to temperature, we're seeing increases in sea level, about 3 millimeters per year right now. More than half of that is due to thermal expansion. So the fact that when water gets warmer, it actually gets larger in terms of volume. It takes up more space. So not only are we melting parts of our cryosphere and adding water to the ocean, the water is warming and expanding. So the water that's already there is literally getting larger, meaning we're going to see increased sea levels. So here we can see our sea levels, change in sea levels from the 1900s through today. We've had a very steady increase in our sea level. And then also ocean acidification. So at the end of this lecture, we're going to get more into sea level and ocean acidification, just giving you a brief overview right now. So our oceans are getting more acidic due to the increase in CO2 in our atmosphere. We'll go over what that means for life in the oceans towards the end of the lecture. So if we look, that is a very, very brief overview of how our climate changes, why our climate has changed, and what's been happening most recently. So if we then extend sort of all those graphs that I just showed you and look at the future, let's think about how our climate changes into the future. So we're going to talk about RCPs, representative concentration pathways, and then we're going to talk about ocean acidification. So understanding what is ocean acidification, what is happening with the change in pH of our ocean, what does this mean for organisms in the ocean, which therefore, of course, affects us because we rely on many of those organisms. And then I will stress that a lot of the effects of these changes are still very, very, very uncertain and a very active area of research. So how does climate change in the future? How do we possibly predict the future? So it takes a lot of data, a lot of thought, a lot of scientists working all together. But what we use are called representative concentration pathways, or RCPs for short. So these are sort of greenhouse gas trajectories for the future based on predictions of population, economics, and energy. So we use these four main RCPs to think about future change. So what the different numbers mean, there's RCP 2.6, 4.5, 6, and 8.5. So what the numbers mean are the radiative forcing increase by the year 2100. So for example, the lowest is RCP 2.6, which means there's a radiative forcing change of 2.6 watts per meter squared by 2100. So RCP 8.5 is the most extreme. This is where we are changing the radiative forcing by 8.5 watts per meter squared by 2100. So of our RCPs, the 2.6 is if we cut all emissions of carbon like 5 years ago, what would happen in our future? 8.5 is the most extreme that we look at. So what if we keep increasing our energy to the point where in 2100 we have a net change of 8.5 watts per meter squared? So which of these scenarios do you think is most likely? So this is CO2 emissions under these 4 different scenarios. So which of these do you think is more likely for us today? Or us in the future, I should say, the way that our global society runs. So I mentioned that RCP 2.6 would be if we cut all carbon emissions completely. We are definitely not on that trajectory. We are not on RCP 2.6. We are actually right on track of RCP 8.5. So what we claim to be the highest, most extreme is really the way that we are trending. So this figure has not been updated since 2015. 2016, some things changed. So this website no longer updates this image, but we are still in 2020 on track with the RCP 8.5 trajectory, meaning we are sort of in our own worst case scenario still. So by 2100, we are anticipating a change of 8.5 watts per meter squared, which, if that continues, translates to a change in temperature of between 3 and 5 degrees Celsius compared to 1900s. That would be horrible. So here are our changes by 2100. So we often use 2100 as a gauge when thinking about climate change. These are estimates. So in RCP 2.6, we see in the blue versus RCP 8.5, the most extreme. We see changes in temperature, increased temperature in all scenarios. So no matter what, we will see an increased temperature, but it's sort of the difference between, are we going to see an increase of 1.5 degrees or 4 degrees Celsius? So that there's a really big difference between these scenarios. So the increase in temperature is totally dependent on the increase in energy due to our greenhouse effect, our global warming. So under these scenarios, we also have ocean pH. So the acidity of our ocean, so we are expecting the oceans to get more and more acidic. Are they going to get a little bit more acidic under the 2.6 scenario, or are they going to get very, very, very much more acidic in the RCP 8.5 scenario? Remember that is sort of the way that we are tracking. Here we have 2 graphs of ocean pH. So between 1986 and 2005 is this one here on the left, and then the future projections of what ocean pH will look like at the end of the century here. So we are expecting some drastic changes in ocean pH. So when we talk about the acidity of our ocean acidification, the pH of the water, we have to talk about what does that mean. So acids and bases. We're going to do just a very quick chemistry recap right here. An acid is something that releases hydrogen ions when it dissolves in water. So H plus is a hydrogen ion. And something that is acidic or considered an acid, when it mixes with water, is going to release hydrogen ions. Something that is a base or basic, when that thing mixes with water, it releases hydroxide ions, which is the OH minus here. So the acid versus the base, does that compound release hydrogen ions or hydroxide ions? So pure water is neutral. It's actually broken up into hydrogen and hydroxide. So when things combine with water, is it going to combine with the hydrogen allowing for the release of hydroxide, is it going to combine with the hydroxide allowing for the release of hydrogen? That determines if that object is an acid or a base. So we have what we call the pH scale. It's essentially a scale of hydrogen ions. So neutral would be right in the middle. It would be a pH of 7. As the pH value goes up, it means there's less and less and less and less hydrogen ions, meaning that that compound is more basic. As the number goes down, so getting closer from 7 to 0, the compound is getting more acidic, meaning that the H plus ion concentration is going up. So taking a look at this figure, does seawater have more or less hydrogen ions than pure water? So here you can find seawater right here compared to distilled normal water. So seawater is going to have less hydrogen ions than pure water. Seawater is more basic than pure water is. So seawater is actually more basic. It's about an 8 on the pH scale compared to a neutral of 7. So how does our atmospheric CO2 have anything to do with the chemistry of our ocean? Well, so the ratio of atmospheric CO2 to CO2 in our oceans is constant. So the ratio always stays the same. What that means is when we increase our atmospheric CO2, say by burning fossil fuels, we're going to increase the amount of CO2 in our oceans, because the more atmospheric CO2 there is, the more of that CO2 that's going to be absorbed by the ocean. So increasing the CO2 levels in our atmosphere increases the amount of CO2 we have in our ocean. That carbon dioxide will then react with water, creating other molecules, carbonic acid specifically, which is going to release hydrogen ions. So now our increasing CO2 in the atmosphere increases our CO2 in the ocean, which leads to an increase in hydrogen ions, which means our ocean is getting more acidic. Our ocean water is going to move towards the higher H plus concentration. So our ocean is going to get more acidic. In order to combat that, the ocean is going to the ocean is going to use carbonate ions to react with the hydrogen ions. So all of these additional hydrogen, not all of them, some of the additional hydrogen ions are going to react with carbonate ions in our ocean. This is going to try and balance out the additional H plus in the ocean. However, a reduction in the carbonate ions is very, very, very bad at a certain level for our oceans. So, in summary, increased carbon dioxide in our atmosphere causes increased carbon dioxide in the ocean, which causes increased hydrogen ions or acidification of our waters. That additional acidification of the waters, those hydrogen ions, are going to react with carbonate ions that are already in the ocean, which causes a removal or a reduction of the carbonate ions that are normally available in our water. So what does that mean if we're reducing the carbonate ions? There are many, many, many organisms in our ocean that need that calcium carbonate to create their shells and their skeletons. So because of ocean acidification, we are removing the calcium carbonate that would otherwise be available for these organisms to create their shells and create their skeletons. So when our ocean waters have enough carbonate, these things can thrive, they can live, they can make their shells, they can make their skeletons. However, When the waters are undersaturated or we don't have enough carbonate, the shells actually start to dissolve. So an increase in our atmospheric CO2 causes a reduction in the carbonate available in the ocean due to this acidification. This makes parts of our ocean water undersaturated in the CO2, meaning not only will new organisms not be able to make shells and skeletons, but it actually is going to dissolve the shells and skeletons there. So a lot of organisms would not be able to live in this undersaturated conditions. So here we have a graph of saturation from 1976 to compared to here on the right is 1995. So take a look at this and see where have these saturation levels dropped to a point that is very dangerous for the organisms that rely on this carbonate, meaning less than 2 on this scale. So less than 2, which I have this arrow to show, is a point where these organisms are going to have a very, very, very hard time surviving. So where in U.S. waters, I should clarify, that's what I'm asking, is where in the coastal United States are we seeing values now where these organisms are not going to be able to survive? So you want to look at the blue colors. So lower than 2 is where these organisms are not going to make it. So the dark blue, even the pink, we can see around the U.S. we have that off the southern coast of Alaska and the western coast of Washington State. So already in 1995, some of the waters around the United States are so acidic that organisms will struggle to live. So now if we extend this graph in time, here we have 1700s, here is 1995. If we then predict what the acidification will look like, what the acidification will cause in 2040 and then all the way out to 2100, you can see that the blue colors on this graph, remember blue is where we need to start being worried about calcifying organisms, really expands. So we will see a lot more of our oceans not allowing for these organisms, including corals, so coral reefs. So that's why in these figures we have shallow coral reefs as black stars, deep coral reefs as pink stars, and you'll see that a lot of those coral reefs actually are going to be in water that will not allow them to continue to survive in the future. So ocean acidification, it is happening. Now we know what's happening in terms of chemistry, but what does that mean for the life in the ocean? So I've mentioned those calcium carbonate requirements. So there's a lot of organisms in our ocean that require the calcium carbonate, including corals, including a lot of sea urchins, coccolithophores, as well as mollusks. So mussels, scallops, and crustaceans like crabs all rely on calcium carbonate. So if we continue to increase the CO2 in our atmosphere, we are going to continue removing calcium carbonate from our oceans, therefore making it more and more dangerous for these organisms. So there have also been studies that show acidity and lower pH in our oceans actually change or have effects on the health and the metabolism of other organisms. But this is still an area of active research. There's a lot of uncertainty with how ocean acidification will affect life in the ocean, in addition to just the organisms that require calcium carbonate. there's a lot of other effects that have not yet been discovered or studied. So if we look at the change in ocean pH, remember the pH of the ocean is a bit basic. It is around an 8.1. So we have seen some changes in the past. So this time scale is millions of years. So 0 is today, and then going back in time to the right. So, to the left. So we've seen a lot of changes in ocean pH in the past. However, right now we are seeing very significant decreases. And if we're looking out in time to 2100, the projections show a change greater than anything we have seen in the last 300 million years. So this would be a very, very, very big change for our oceans, and it's happening quite quickly. So the real question with ocean acidification and where a lot of the uncertainty lies is, will life in the oceans be able to adapt? So will life adapt to the change in pH? So the problem, one of the main problems, is that the rate of change is what's important. So we are changing the pH of the ocean incredibly quickly. So then the question begs, will the organisms be able to change quick enough that they will survive this change in pH in our oceans? So what normally keeps the pH stable? Well, generally, if the pH of the water changes, it becomes undersaturated with those carbonate ions. The calcium carbonate in the sediments on the bottom of the ocean will dissolve. So if the water is undersaturated, sediments on the bottom of the ocean will dissolve and add that carbonate back into the water. So when the water is undersaturated, it is able to saturate itself back. It's able to balance itself out by dissolving sediments on the bottom of the ocean. However, this happens very, very, very slowly. So in the past, the ocean has not changed in pH very quickly. So this dissolving of sediments has been able to allow the ocean to stay at a very stable pH. What's happening now is that we are changing the pH much, much, much faster than the ocean can balance itself out on its own. So we're changing the pH much too quickly for the natural fix of acidification to occur. So that is proving to be quite dangerous for a lot of the organisms in our ocean. So next, let's talk about the ocean warming and sea level rise. So the big concerns with climate change in our future are that ocean acidification, the rate of ocean acidification, and then of course also sea level rise. So this is our last topic for today. Actually, this is our last topic for the whole class. So we're going to talk a little bit about sea ice. We will talk about sea levels, how they are rising, how that affects coastal communities, and then we'll go over the different causes of sea level change. So sea level rise is already happening. Sea level rise being literally the rising of our sea levels. It is a direct result of climate change, of increased warming. So we are seeing sea level rise. We're also seeing the rate of sea level rise increasing, and we're expecting that to continue accelerating in the future if we continue on this RCP 8.5 trajectory. The rate of sea level rise is going to greatly depend on the future of our greenhouse gas emissions. So in order to combat sea level rise, we need to either adapt or mitigate all of the coastal changes. So our coastal regions have a very high population. There are a lot of people that live near our coasts. About 150 million people live within 1 meter of high tide. 250 million people live within 5 meters of high tide. There's a lot of people. There's a lot of infrastructure right at our coastline. Ports, power generation, transportation, cities, all built right along our coastlines. So this is a graph of loss in the case of 1 meter of sea level rise. So loss of population, loss of land area, and loss of GDP in US dollars. So Asia would lose the most land area, as well as displace the most people, and it would be the costliest. We can see North America here. We are second in losing land area. All around the world, we have 150 million people within 1 meter of high tide. So if our sea levels rise by 1 meter, those 150 million people are going to be flooded. They are going to have to move. All of those people will be displaced. They'll have to move inland, away from the coasts. So what causes our sea level rise? There are a couple different causes that all work together. So first, we talked about this a little bit, glaciers. When our ice melts, that water is added to our oceans. Increased water in our oceans is going to raise our sea levels. So glaciers and ice sheets, so actually 1 and 3 here, are going to increase our sea level rise, increase our sea levels as we continue to melt the ice on Earth. The next reason, or the next cause, is called thermal expansion. So this is what I mentioned at the beginning of class, where as water gets warmer, it actually physically expands in terms of volume. So as water is warmer, it's going to expand. It's going to take up more space. So as the oceans are warming, because remember they are absorbing 90% of the additional heat, the oceans are warming, the ocean is actually expanding. It's thermally expanding. So that is about 50% of our current sea level rise is caused by thermal expansion. And then the last and smallest cause of global sea level rise is groundwater removal. So removing water from our continents. So removing water can actually cause our land to sink down a little bit, and we're not putting water back into the continent. So we are pulling water out. It will eventually run off as some type of wastewater back into our oceans. So we are adding water to our oceans from glaciers, ice sheets, and our groundwater reserves, as well as the water in the ocean is warming, so it is expanding. All of these things are going to cause the level of our oceans to rise. So what is going to happen if we just continue extracting more and more and more groundwater? What do you think? Are you listening? So as we pull water out of the ground, using our wells, let's say, what's going to happen to the sea levels? Oops. So if we're pulling water out of the ground and we are not pumping water back into the ground, that means that water is going to add to our oceans. So we're adding water to our oceans. Not only that, but sometimes the land will actually subside. The land will actually sink a little bit as we pull water out of the ground. All of that would cause, of course, additional sea level rise. So here we also have our glaciers and our ice sheets. So this is the same figure that I showed you guys before. Here we have Greenland and Antarctica, our 2 ice sheets on Earth that are losing mass with time. So as this water melts off of the continents. It's going to add into the ocean. We are just adding water. The sea level is going to rise. So here's my question. It's a trick question that I really, really want you to remember from this class, is the difference between sea ice and land ice. So sea ice is ice that is floating on the surface of the earth, on the surface of the ocean. I have the answer here for you already. Does sea ice contribute to sea level rise? So if sea ice is already floating in our ocean, it is not going to cause sea level rise. It is already in the ocean. It is already floating. It's already displacing its volume. So the only way that melting ice contributes to sea level rise, is when it melts off of a continent. So when there is ice on land and it is melting and flowing into the ocean, that is where we have an increase of water in the ocean. If there was ice already floating here in the water, as that melts, it actually doesn't cause a change. So the way that we change our sea level with ice is if we are taking water out of the ocean or putting water into the ocean. So in our case now, all of our land ice is melting, all on the melting path with our warming. So that water is being added into our oceans. So sea ice, ice that is floating, does not contribute to sea level rise. Only ice on land as it melts will contribute to sea level rise. So that's a really common confusion when we talk about sea level rise. So here we have sea level change from 1700s up to just a couple of years ago. So there was essentially no change between 17 and 1900. There's really no change between about 0 AD and 1900. There was no change in sea level. However, over the past century, we've had a sea level change of 1.7 millimeters per year. And the rate of increase is actually also increasing. So not only are our sea levels rising, but the rise is accelerating. So in the 20th century, we had a sea level rise rate of about 1.7 millimeters per year. Since 1993, however, sea level has actually been rising at a higher rate of about 3 millimeters per year. So we are expecting sea level rise to continue and for this rate to increase. So this table here shows sea level rise in millimeters per year, and it's broken down into the different factors. So this is a cool table. They're able to actually show you exactly which factors cause the sea level rise that we are seeing. So what contributed the most to sea level rise between 1993 and 2010? Take a second to read the graph, try and figure that out. So if we look at 1993 to 2010, we actually see that sea level rise was mostly caused by thermal expansion. So thermal expansion has been the thing to cause the most sea level rise in recent years. Sea level rise in the future. Oh, I should mention that in the future, it's expected that the ice sheets, Greenland and Antarctica, are going to be the most impact. So thermal expansion, the water is only going to expand so much. So at some point, with continued warming, thermal expansion will actually stop expanding. And glaciers in Greenland and Antarctica, those ice sheets will increase their sea level rise potential. So in the future, we are expecting Greenland and Antarctica to be the highest causes of sea level rise. So if we look at our projections of sea level change based on the RCPs that we talked about, we see that even in the RCP 2.6, so the best case scenario, we still are seeing sea level change. So by 2100, we would still expect a sea level change, even with that RCP 2.6. But you can see the RCP 2.6 is the purpley blue line. The 8.5 is here in the red line. So we can see much higher sea level rise expected by 2100. This is a graph produced by the IPCC, the International Panel on Climate Change. Those that study the cryosphere, such as myself, would say that these are a bit low. Most are expecting for sea level rise to be higher than 1 meter by 2100. So if we look past 2100, so a lot of what climate scientists do is we look out to the year 2100, but as we're getting closer and closer to 2100, it's already 2020, we're starting to have to expand our projections out even further. So sea level change is plotted here compared to 1990. So we see the 2100 values. This is in centimeters. So we're expecting about 1 meter of sea level rise by 2100. But if we go out to 2300, it's up by 3.54 meters of change expected. So sea level rise is going to have very bad consequences for many people. We're expecting it to continue in the coming centuries. So just because many of our graphs stop at 2100 doesn't mean that the sea level rise is going to. There's going to be a lot of planning, mitigating, adapting that has to happen due to the changing of our sea level, the changing of our coastlines. And it's not going to be an easy task. So locations can be really, really, really difficult to calculate the risk of certain locations because there are so many factors that come into play when we think about the future of sea level rise. So we have to think about the land. Is it stable land? Is it subsiding or sinking land? Is this also a location that experiences storms? So remember with our hurricanes, if there's more water in the ocean and we're expecting our hurricanes to become more intense, we can expect more of a storm surge. Is there higher land around? So is there land for people in these coastal communities to move to? Are there resources for water there for these people to move? How developed is the coastline? So how many people are there? How many buildings are there? Are there entire cities that need to be uprooted and moved somewhere else? That just gets more and more and more expensive. And then also, depending on the country, depends on that changes how much money is available to make these changes, to make these adaptations. So the resources that the country has to make any sort of adaptation to change also changes the way we think about risk. So depending on so many factors is how we think about the consequences or the risk of sea level rise to different countries, different coastlines, different locations. So how do we reduce the impact? How do we help? How do we stop this from happening and affecting those 150 million people that live within 1 meter of the coastline? Really, the only way to do this is to reduce our greenhouse gas emissions. So we have to reduce the greenhouse effect to reduce our warming and therefore reduce the predicted sea level rise and lower the predictions or the projections of our future sea level rise. So something really, really, really cool is the Paris Agreement. So 190 countries came together and signed the Paris Agreement in 2016. So What this means is all of these countries are agreeing to limit our temperature change to below 2 degrees Celsius. So all of these countries are saying we are going to work towards limiting the warming to 2 degrees maximum, trying to increase the ability to adapt to the effects we know are coming from climate change, and also limit the horrible effects that we see from climate change. So these countries made finance decisions to keep the future. They made a lot of promises, I can say, to lower greenhouse gas emissions and help with making climate resilient development. So anything developed in the future has a more climate resilient awareness. So there were a lot of countries that came together and said, yes, this is essential. We need to limit our greenhouse gas emissions globally. It's not something that just one country can do. However, there are a few of the really big countries, ours being one of them, that make a huge dent in that greenhouse gas emission. So this came into effect in November of 2016. Oh, it was 194 countries. So it was signed by 194 countries and the EU. So it's cool because it leaves some freedom. So each country gets to decide how they're going to cut their emissions. But then they had to make a public commitment. So then they had to announce how they're going to do it. They had to announce their plans of how they're going to cut their emissions. But each country was allowed to say, each country was allowed to decide the way that they're going to do it that best works for that country. So this is awesome. Climate scientists all over the place were really, really excited to see this global commitment, this global agreement to not only recognize the problem, but try to come up with solutions that work for everyone, that work for all of these countries. However, sadly, on June 1st, 2020, our administration withdrew from the agreement. So the US is no longer taking part in the Paris Agreement, which is a huge problem because we are a very big country that produces a lot of greenhouse gases. So this was a big blow to the climate scientists around. We were all really, really bummed out. But the cool thing is that we go to school, or you go to school, even if you're not there right now, in California. And California is an awesome state that has said, even though we are not in the this Paris Agreement anymore, it doesn't mean we're changing anything. So California has already made a lot of commitments to reducing emissions. So by 2020, the goal was to be below 17% was to be 17% below the 2013 emissions. And by 2050, the goal is to be 80% below the emissions from 1990. So California has some very, very aggressive targets in the best way possible. They are going to, we're making a lot of changes in fuel, low carbon fuel and renewable energy, and zero emission vehicles. So for a while you could get a big tax break, for example, if you bought an electric car. There are some tax incentives for getting solar panels on your house. So California is doing a lot to encourage people and companies to make more climate conscious decisions. So I do really like that, even though, and California is not the only state, I should say. I'm just focusing on it because, of course, it's our favorite one. It's where we are. California has said, even though the country is no longer in the Paris Agreement, we are still going to abide by our commitments because we know that that is the right thing to do. So California is a wonderful place. But what can you do? So as an individual, I really like this illustration here. So as an individual, what sort of things can be done? I just have two ideas here. So understanding the principles and the fundamental concepts about our ocean is really important to being able to understand what's going on, what's going to happen in the future. So you can check this one off because you took this class. So you learned those fundamental principles and the concepts. You can continue reading. You can learn more about oceanography online. If there was any part of this class that was super, super exciting to you, there's a lot of research out there for you to learn more. But now you have sort of the basics, the real essential basics of oceanography to understand what's happening with climate change in our oceans in the future. And then the second thing that you can do as an individual would be make informed decisions. So make informed decisions and responsible decisions in terms of our ocean. So our ocean and the resources, make informed and responsible decisions. So now that you know, or as you continue to learn, you can continue to make these responsible decisions to help our oceans stay as absolutely wonderful as they are today. So here is my last figure for you all. Temperature anomalies, so by country, so by year and by country. Here we're in the 1960s. Here we have the global temperature also plotted here. So as we go through time, you see that each country has reported warmer and warmer and warmer temperatures as our temperatures have continued to increase globally. I really like this this figure here because it's very easy to understand once you know what you're looking at. The way that they use the colors, the way that they use the bars, making them larger, and the way that they have every country. So it's very interesting to see not just split by continent, let's say, but by individual country. We can see the temperature changes very clearly at the end when we get closer and closer to the present. The figure is more and more red, showing that increase in temperature. So our climate is warming. I just hope we can help out our oceans. So for my last words, I will have to say a huge thank you to Chris, our TA, for all of his help, for doing some great lectures last week, for always being super handy in our discussion sections, helping each group. And a thank you to all of you. So this is a crazy time that we are living in. A lot of things are different from the norm, from what we were expecting. I would even say this could be a fairly difficult time, but you still took the class. You still hopefully had fun in the class. You learned something interesting. At least one thing interesting, I hope, from this class. So thank you all for all of your work these past 5 weeks. I know a 5-week course is a crazy amount of material to cover in 5 weeks, but it is nice to get some credits out of the way in the summertime. I'm glad that you were on this remote ride with me through this class. I hope that from this class you take away an appreciation for our oceans, so the complexity, all of the interconnected pieces of our oceans, and also take away the importance of protecting our oceans. So protecting the oceans, protecting the ecosystems into the future. So thank you guys so much. I hope you enjoyed the course. And that's it. We're done. I'll see you for our very last discussion section on Thursday at 10:30. That'll be our last one. And then the final is on Tuesday. So Tuesday we have our final. It'll be open all day just like our other exams. So thank you all. Have a good day.